scattered particle and there's two names, right? One is scatterer, the other is scattering. I don't know, scatterer or something.
Scattered particle. Okay. Let's start from the beginning of the semester. So we are doing perturbations. Okay, there's a time-independent one, time-dependent one, and in the last several weeks we were looking at time-dependent perturbation. Where we have some potential that depends on time, and we were calculating various transition rates, and we looked at potential that depends on time, but we also looked at potential that don't depend on time within time-dependent perturbation theory. So they just have trivial time dependence. They don't change in time. That's also a time dependence. So one of the results we had was, for example, one of the things we were interested in is the transition rate. Which was basically, let's say that you have your system, you turn on some potential. Once you turn it on, it might be constant in time. It might also have some non-trivial time dependence. And then you ask yourself the question, if you created your system at the state I, what is the transition rate per unit time? Well, the rate is per unit time that it will make a transition to a final state N. So that was one of the questions we were asking. And one of the results we had obtained, at least in first order perturbation theory, was this transition rate was given by 2 pi over h bar v and I squared, and there's the energy conservation. This is if V is independent of time. And this V and I was the matrix element of the potential. Now, if you remember our derivation of this result, what we had done was we were looking at the general solution. We defined what we called interaction picture. Which was defined as, let's say that we have a system that is in the state alpha at the time t0, and we ask ourselves the question, what is the state at that final time t? In the interaction picture, this is defined in this way, in terms of the Schrödinger picture states. So you see, if this is in the Schrödinger picture. Now, alpha t0 t in the Schrödinger picture is e to power minus I over h bar h of t alpha t0. T minus t0, sorry. So you see that if there is no potential, if h and h0, they are equal to each other, the interaction picture state basically doesn't depend on time. In fact, it is nothing but the Heisenberg picture state. And any time dependence of the interaction picture is due to the potential. And in fact, we had also shown that in the interaction picture, this time dependence can be written as a time-ordered exponential h bar from t0 up to t, vi of t prime dt prime. Well, this is basically an easy way to remember what the expansion is, but it doesn't really help much, because eventually if we want to calculate this, we have to again make this expansion. And this vi of the interaction picture operators are defined in this way. So we are always assuming that we can actually solve H0. So if we can solve H0, we can determine what these interaction picture state operators are as a function of time. So that is the part we already know. The part that we do not know is how the interaction picture states evolve due to the presence of V. And in fact, what we had done up to first order, well, this is one minus I over h bar from t0 to t, vi of t prime dt prime, plus all the other states, alpha of t0. And then we say, okay, this is valid in general. Now, if we have an eigenstate of h0 as our initial state, then this, the transition probability from an initial state I to a final state N, that is basically this overlap, which is, we have Kronecker delta I N minus I over h bar from t0 to t, and vi of t prime I dt prime, plus, of course, all the other terms in the expansion. If v is small, it's enough to keep just the first term and ignore the other terms. And this vi of t using the definition of the interaction picture operator, this is just e to power I en minus ei over h bar of vni. So this is the matrix element we have. So if you go back to this matrix element, assuming n is different than I, we are just looking at transitions to other states. This would be minus I over h bar vni from t0 up to t. So this was the amplitude. Now, if you remember, we did basically two things. One, this is the amplitude. If we would like to calculate the probability, we have to take the absolute square of this probability. And we are not looking at the transition probability itself, but the rate of transition, the transition rate, which is the time derivative squared. Well, we can just write it. Let me just calculate it in a slightly different form. This will be equal to, from t0 up to t, dt prime e to power I omega ni of t prime. And then another from t0 up to t, dt prime e to power I omega ni of t prime. And we will be assuming that t0 is very far in the past. We are at a much later time, t. So one of these integrals is essentially would give me a 2 pi times Dirac delta and I. But if I replace one of them with the Dirac delta of omega and I, well, the time derivative would just give me, the other one will just give me 1. So there's a minus somewhere. No, this shortcut basically doesn't work. Anyway, so this squared. So here, from t0 to t, dt prime e to power I omega ni of t prime, absolute squared, the time derivative. Well, we first showed that this was sine squared something divided by sine squared omega ni t divided by omega ni squared. And then we said that, okay, that is in the limit of t very large, it's basically a Dirac delta. So for large t, and t0 goes to minus infinity, This is 2 pi Dirac delta of omega ni times t. No, sorry. It is this one. Basically, it's 1. Well, what I was trying to do before, we can also do that. So this is equal to from t0 to t dt prime e to power I omega ni of t prime dt double prime for t0 very far in the past, t very large. This is essentially 2 pi times Dirac delta omega ni. If you put omega ni equal to 0 in the first integral, this exponent becomes 1. Well, it's t minus t0. If you take the time derivative, it just gives you 1. So d by dt of this one is just 2 pi Dirac delta omega ni, or 2 pi h bar Dirac delta en minus ei. And then we recover what's called the Fermi's golden rule, this one. And then, okay, this was the general theory. Then we looked at problems. Okay, here, this is an example where V doesn't depend on time explicitly. Then we looked at a potential which has a harmonic dependence. So basically, we have V was some constant in the sense that it doesn't depend on time. It might depend on position operator or momentum operator, but it doesn't depend on time. E to power I omega t plus nu dagger e to power minus I omega t. And then we have seen that one of those terms describe the absorption of an energy h bar omega by the system. The other one is leads to emission of an energy h bar omega by the system. So these are two examples of stimulate. One is the absorption. The other one is stimulated emission. You apply an external potential. You send an external photon, in a sense, if you like. And then the system, due to the presence of this external photon, the system basically emits a photon. It doesn't absorb it, but it emits another one with the same energy, which is the basic principle of how lasers work. That's called stimulated emission.
Sure. One photon passes near our system and it emits a photon, right? But what happens in quantum field theory? Because you always have virtual photons popping up you have virtual photons that can pop up all the time. So why don't atoms continuously emit radiation?
Well, you see this Dirac delta, right? Now, where was it? Okay, this Dirac delta. In the case of absorption or emission, you get plus minus h bar omega. That is the main difference between the previous case, where the V was time independent, with this case where you have the harmonic dependence. So if you want the emission, there should be a state that the atom can go into. In fact, why do we have spontaneous emission? You saw the hydrogen atom. You have all the excited states. They are eigenstates of the hydrogen atom. But still, if you create a hydrogen atom in an excited state, it will emit after some time. If it's an eigenstate, it shouldn't change. We are not applying an external potential to our system, so our system is unperturbed in principle. So the excited state is an eigenstate of the Hamiltonian hydrogen atom. So it shouldn't emit, it should stay there, but it doesn't. And the reason is, in fact, just because what you said, the vacuum is constantly, there is the photons, there are all these quantum fluctuations. So although there are no particles, there are no photons we are sending, the electromagnetic field is still there. The vacuum has an electromagnetic field, and that field causes the emission of the spontaneous emission. In fact, because of that field, although we are finding energy eigenstates of our very simplified Hamiltonian, it is not actually the eigenstates of the full field theory.
Okay.
So that is why, since it's not an energy eigenstate, it changes on its own.
Are there eigenstates of full field theory?
Well, there are eigenstates, definitely. The question is, do we know those eigenstates? Well, if you look at free field theory, then we do know the definite eigenstates, nothing changes. But I don't know if we know any eigen solution of any physically viable field theory, let's say. I mean, as far as I remember, there was a book of exactly solvable field theories. So definitely we know the eigenstates. But I mean, if you ask me, do we know the energy eigenstates of the standard model? No. We know approximate solutions. We don't even know the vacuum of QCD.
I was just going to ask, for QCD we don't even know if eigenstates exist or no.
Well, the eigenstates always exist.
So what don't we know about QCD?
What is the eigenstates? What are the eigenstates? We know they exist, they have to exist, and they form a complete set. But what are the eigenstates? A proton is an eigenstate. But the proton state also has all these fluctuations around it. So if you ask me to write down the exact eigenstate of some field theory, I won't be able to write it down. I can write the proton state, but I cannot write down all those fluctuations. I can calculate the correction due to those approximately using these techniques.
So the big open problem in QCD is this one. There's a big open like clay mathematics type problem in QCD, right? Is this it? Not when you write this?
No, this big open problem of QCD is the mass gap.
Ah, okay.
Is it confining? And any other questions about the topics of this course? Now, once we had the formalism, okay, we had the time-independent potential, potential with harmonic time dependence. We sketched basically, we looked at transitions from discrete states to discrete states. We looked at transitions from discrete states to continuous states, that is the ionization. So initially you have an electron bound to an atom. You know their wave function. And then the final state will be an electron that's not bound to an atom, which will be approximately a plane wave. And now we will be, what we mean by scattering is mainly we have an unbound system, unbound electron in the initial state, and an unbound particle at the final state. So any questions up to here? So we will look at these transitions. Let's say we send a particle with wave vector k, and what is the probability that eventually we will get a particle with the wave vector k prime? What is the transition rate for this? And we also define another concept, the cross-section, the cross-section, which we had defined as the transition rate over the influx of particles, initial flux. And at least in the classical theory, this definition does correspond to an actual physical area. Now, I will not repeat that derivation. So any questions up to here? Or anything else you would like me to repeat in more detail? Because we will basically pick up from here and develop our scattering theory. Now let me pick up this term. Let me also add the Kronecker delta NI piece. So what I will be imagining is, so here we have some scattering center. It can be an atom or another proton, another particle somewhere over here. And I will be sending some other particles into this region. And I will put my detector at a somewhat far away region. So this is my scatterer. So I'm sending my particles. And my detector is somewhere over here. So I will be calculating the cross-section from this process. Yeah, you see, this detector can be your eye. It can be some sophisticated detector at CMS, or even your eye is a detector for us. Now, we know that this part, well, let me modify my notation a bit. So this is what I'm looking at.
Over the omega here and then I. So you modify it?
No, that is the omega. Omega kk prime. Okay. Well, let me write IF initial final. Now, this is, of course, an approximate solution. And what I will be imagining is I would like to set t0 goes to minus infinity. Because you see, if you look at my process, I create my particles at the far past, and I will be measuring my particles in the far future. Now, far past and far future doesn't mean several years ago and several years afterwards. It can be even a few seconds or milliseconds. The important thing it will be how much time it will spend within that region. And the time, earlier time is much before that. It can be a few milliseconds also, and the later time will be much after that. Again, it can be just a few milliseconds. Considering that for example, in LHC, we have collisions every nanoseconds. So within a nanosecond, the collision, one collision is already over. So those are the time scales. And when I'm talking about far past, it is a time scale much earlier than nanosecond. Now, so I will be sending t0 up to infinity, minus infinity. Now, I want that to be convergent. So I just introduce some, let's say, plus epsilon t prime. So that eventually I will set epsilon to 0. And epsilon t, you see, I'm turning on my interaction in a sense. In the past, I'm turning it on slowly, and it reaches full power now. Well, the interaction is basically happening now. That is what I will be imagining. But that means that epsilon t is now, is approximately 1. Or let's say much less than 1. So I'm turning the interaction slowly with time. Although I said my potential was time independent, I'm basically adding a time dependence, an artificial time dependence, so that I'm turning on my interaction very slowly. It reaches the full power, its full power now when the scattering is happening. And since I'm interested in the transition rate, well, I only care about it should only depend on what my potential is now. Because transition rate should turn out to be independent of time. And eventually, I'm also interested in sending t goes to infinity. But if I want to take this limit, I have to first set epsilon goes to 0. So that's the order of how I will be taking the limit. So first I will make my computation as a function of time. Then I will take the limit epsilon goes to 0. Then I will take the limit t goes to infinity. Now, here again, this matrix element over here is approximate. I have infinitely many terms. So let me do one more thing. This k prime k. Let me drop the t on the left-hand side. Just keep in mind that it's at the time t. Let me write this as k prime minus I over h bar t k prime k from t0 to t dt prime e to power I e k prime minus e k t over h bar. Now this is not approximate, this is exact. I know that this will give me the Dirac deltas and the rest. Any other time dependence or anything else will be within this matrix element. At least I know one thing, that up to first order in V, I'll just compare these two expressions, this one and this one. They look almost the same. One has V, the other one is T. I don't know what that T is yet, but that T basically contains all the ignored terms in this expansion. I'm summing them all up into this T. Now the transition rate, I already know what the transition rate is. This will be 2 pi over h bar. Squared, and then we have the energy conservation. This I already know. Now I can write the cross-section. But I know the transition rate. Remember, the cross-section is the transition rate per incident flux. What is the incident flux? Now, I will be dealing with plane waves. And, well, I have two choices, basically. Either I can assume the space is infinite. The momentum k can take continuous values. In that case, of course, this Kronecker delta will also be converted to Dirac delta. That is one option. Another option is I can use a finite volume, a very large but finite volume, and normalize to one particle within this volume. And then I don't need to worry about the Dirac deltas, but this will remain a Kronecker delta. I can normalize my states to 1. Both should give it the same answer. So I will stick with the derivation in your book. I will use just a box normalization. So if you like this Rk, the states will be e to power I k dot r over L to the power 3 over 2. You can just go ahead and calculate the flux corresponding to this wave. Or, is it in general, flux is just the density times the velocity. This is always our flux. Well, the density of my particles is, well, plane waves have uniform density. So I have one particle within a volume L cubed. And the velocity of this particle is what's the velocity of this particle? Yeah, this is my flux. Now I can write my cross-section. Well, let me write d sigma. This will be 2 pi over h bar t k k prime squared Dirac delta ek minus ek prime divided by h bar k over m 1 over L cubed. 2 pi over h bar squared m over k t k k prime squared L cubed. So this is what I obtained for the cross section. Now the reason why I called it a differential cross section is, you see, this is the scattering cross section for one particular final k prime vector. So if you want your particles to scatter into one particular specific direction, you have to have a very small area that you should target. And in fact, for practical reasons, you will never be able to measure such a small differential cross-section. What you will actually measure is the scattering into some final states within a given direction. So what you will actually measure is the sum, k prime, such that k prime lies within the omega. This is what we can actually measure. So do you have any objections to this expression? Keep in mind that eventually we will set L to infinity.
We should get rid of the L cube, and it comes from the T.
Well, you see, L cube seems to be problematic because, I mean, problem shouldn't change, the physics shouldn't change if I just change the volume I use to describe my system. I have my interactions over here, let's say, in this very small region. And whatever is happening over here shouldn't depend whether I describe this very small region within the volume of this classroom or within the volume of this whole building or within the whole universe. Whatever is happening over here should be independent of what happens somewhere over there. So L shouldn't change the result. In fact, L doesn't change the result because keep in mind that Tkk prime, which will be Vkk prime, at least in first order, this is K prime Vk, which will be d cubed r e to power I k minus k prime dot r over L cubed. This is the normalization. From the normalization of the waves. Remember, the waves three over two. This one? No. That is the product of two wave functions.
Right, then I have 1 over L cube. Then I have 1 over L cube.
Oops. So how do we get rid of that one? Now let's look at this sum. Let's say that we are using periodic boundary conditions. What are the allowed values of K? This should be 2 pi over L, nx, ny, and z, where nx, ny, x, y, and z can take values 0, plus minus 1, plus minus 2, etc. And the sum over all k prime such that k prime is within this d omega and within this direction. Let's say that I can write this as d cubed then, of course with this condition. This will be L over 2 pi cubed d cubed k. which will be L over 2 pi cubed k squared dk d omega. Well, these are all primes. Now let's go back to our expression over here. This is L over 2 pi cubed k prime squared dk prime d omega. Remember, k and k prime, they are also equal to each other. Because of this Dirac delta, k is should be equal to k prime. So I can just cancel one of these. This will be 2 pi over h bar squared m L to the 6 divided by 2 pi cubed tk prime squared. I still have this Dirac delta dk prime squared over 2 d omega. This is my cross section. D sigma by d omega will be, now E of k prime is h bar squared k prime squared over 2m. So instead of integrating over k prime squared, now let me write it down. This is 2m over h bar squared d ek prime over 2. The omega is on the other side. Now I can use the Dirac delta to integrate over ek prime. This will be, let's see if I didn't miss any factors somewhere on the way. By the way, I probably missed some factors on the way. Just make sure that you check those factors.
Can I ask, when we get from summation to integral, what assumptions did we make?
Well, okay, so this is summing over k prime. Okay, so what did I do? I'm summing over k prime. But this is the same thing as summing over n. So I'm summing over n prime. And here I have delta nx, delta ny, delta nz. They're all 1. Then what I did was, since these are the allowed values, delta kx, y or z is just 2 pi over L delta n, or delta n x, y, z is L over 2 pi delta k x, y, and z. So that is what I did when I went from here to here. Now you can still interpret this as this d cubed k prime, well, this whole thing as a summation over k prime. But you see, these are all 1. So delta k will be very small if L is very large. So the only assumption I actually made is that L should be large. Well, which is not reasonable, which is not unreasonable, because eventually I will take L goes to infinity. And now at least the factors of L work out fine. You see T, K, K prime matrix element, we are just seeing that it scales as 1 over L cubed. And I'm sorry, tk. Here I have a v. It scales as 1 over L cubed. And the cross section is L to the 6 times t squared. So it doesn't scale with L. L's dependence cancels. Now, still we don't know what this t is, but at least we know that if we can calculate t, we can calculate the cross section. And the cross section will be basically just the absolute square of t. Again, I repeat, I probably got those factors 2 pi over h bar to the 4 m squared L to the 6 wrong. I have 2 pi cubed also. Yeah. We can check the dimensions. You see? Not really. You see, the T matrix elements of T has this form. So the unit of T is volume. No, it's energy. T has the units of energy because d cubed R has the unit of volume. I am dividing by volume. So this is dimensionless. The only thing that remains is the potential energy. So T has the units of energy. So this quantity has the units of joule squared. L to the 6 is meter to the power 6. M squared is kilogram squared. H bar is joule seconds. So it is joule to the 4 times second to the 4. So let's say this is meter squared divided by joule squared, kilogram meter squared per second squared, all squared. Yes? I separated out 1 meter squared. Out there is a meter squared in the square kilogram meter squared per second squared, but that is joule. So I have in parentheses, I have joule squared divided by joule squared. They cancel. Oh, okay. At least I probably got the factors for it. It's meter squared. Cross section has units of meter squared. The units match. That is, if I miss some factor, it's not the mass, it's not the h bar factors. Other questions?
Cannot there be a process where a scattered particle gains some energy from the scatter?
Now, in this process, no. Because we are basically assuming that V is independent of time. The only time dependence is the time dependence that we introduce by this epsilon parameter. But since eventually we set epsilon goes to 0, we are looking at a time-independent potential. So the system has, as a whole, has a time translational symmetry, although we break it during some at intermediate steps. The problem as a whole has time translation symmetry, which means that energy is conserved. And although the plane wave is not the exact eigenstate of this system, what I'm actually imagining is, initially I have a wave packet that is very far away, and it has an almost exact energy. So the system in the far future should also have almost exactly the same energy. Other questions? So let's give a 10-minute break and we will continue after the break.